Johan got kicked out. Whoops, Johan, come back. All right, so 11.4, we're going to talk about the equilibrium constant for water, for acids, and for bases, or what we call Kw, Ka, and Kb, which is Kw, something you've seen before. So let's get a little refresher. In our acid-base unit, we talked about the Kw, or the equilibrium constant of water. We said that the Kw is equal to the products over the reactants, but our reactant is a liquid, and solid and liquids don't affect our equilibrium, so that's over 1. And then, do you remember what this is equal to? 1 times 10 to the negative what? Feel free to chime in on chat. So Kw, or equilibrium constant of water, is the hydrogen concentration times the hydroxide concentration, which is equal to 1 times 10 to the negative 14. So I really hope that looks familiar. Just a real quick refresher on that. So this is something we've seen before, and it's this equilibrium constant. So what's going to be new to us today is the equilibrium constant for acids, or what we call Ka, and the equilibrium constant for bases. And so the equilibrium constant for acids, things we need to know, our hydrogen ion is always in the numerator because hydrogen is a product of an acid ionizing. This is huge. Very few hydrogen ions are going to be formed from an acid at equilibrium, and we're going to leverage that mathematically. The answers you get, what do they mean? Well, if we get a really large value for Ka, that means that more hydrogen ion is produced at equilibrium, which means it's a stronger acid. The smaller the Ka, the weaker the acid is. And then just a quick refresher on some of our old formulas. The formula for pH, our Kw, and then our formula pH plus pOH equals negative 14. So how we do these, if we want to write the equilibrium expression, and remember, if you have questions at any point, go ahead and let me know in the chat, and I will stop and answer your questions right away. So writing the equilibrium expression, if we have our generic formula for an acid, our acid, which we call HAH plus some anion, is in equilibrium with the hydrogen ion. This is what truly makes something an ion, or excuse me, an acid, is the fact that it produces a hydrogen ion plus the anion. So we write our Ka expression as the concentration of the hydrogen times the concentration of the anion over the concentration of HA, our acid. So that's our expression. What can we do with this? Well, we can find the pH. If we know the concentration and we know the equilibrium constant for the acid, we can determine the pH of this solution at equilibrium. So we're going to make a rice table. We have our reaction. We're going to go for initial, change, and equilibrium concentrations. And we're going to fill in our table with what we know. I'm going to go ahead and switch colors. So what do we know? We know the concentration of our acid, which is 0.250 molar. Initially, we have no hydrogen and we have no anion. And we're going to make an assumption like we did last week. Our change, we're going to lose concentration of the acid, and we're going to gain hydrogen ions, and we're going to gain anions, and we'll call those X. So then at equilibrium, that means that our concentration of HWO3 is going to be 0.250 minus X. Our hydrogen ions concentration will be X, and our anion concentration will be X. So what do we do once we're here? Well, we can plug into our Ka expression. So I'm going to write that over here in the corner. That is hydrogen ion over our anion over the concentration of HWO3. Remember, if any of these had coefficients, they would be raised to their coefficients. And all their coefficients are 1, so I'm neglecting to write the 1. All right. I'm going to plug in our equilibrium values into that expression. So I get Ka is equal to X times X over 0.250 minus X. All right, here's where I'm going to stop. Very few hydrogen ions are formed. As this is written right now, to solve this, you're going to have to do a quadratic equation, which can be done. However, we can make an assumption that allows our math to work out. Very few hydrogen ions are formed. That means if very few hydrogen ions are formed, then our equilibrium concentration of HWO3 isn't significantly less than 0.250. If it's not significantly less, then the assumption I can make, I can assume that X is a very small number. If X is a very, very small number, then 0.25 minus X is still 0.25. So I can go in here and I can make a mathematical change. I can say the Ka is equal to X times X over 0.25 because X is very small. If I declare that I'm making that assumption, I can go ahead and get rid of it. Now I don't have to do the quadratic equation, and it's much easier to solve. So this Ka, we're told what it's equal to. It's equal to 7.2 times 10 to the negative 6th. How do I get X by itself so I can solve for it? Well, first I can multiply both sides by 0.250. Then I get that X times X, or X squared, is equal to 7.2 times 10 to the negative 6 times 0.250, which is 1.8 times 10 to the negative 6th. How do I get X alone? I take the square root. Square root of that, I get X is equal to 0.0013. So what does this number mean? 0.0013 is the equilibrium concentration of our hydrogen ion. Well, pH is equal to the negative log of the concentration of our hydrogen ion. If I now know the equilibrium concentration of hydrogen, I can find the pH of this solution. So I can say pH is equal to the negative log of 0.0013, and that is equal to 2.9. In the chat, will you let me know if we have a pH of 2.9, is that an acid, a base, or neutral? So what is a pH of 2.9? I'll go ahead and pause here. Excellent. See many of you chiming in, that is an acid. All right, before I go on to talk about Kb, what questions can I answer for you about Ka? Is there anything you'd like me to explain in more detail? And feel free, if you do have questions along the way, you can type in chat and let me know as I'm going along. So anything I can answer for you about the equilibrium constants of acids before we talk about the equilibrium constants of bases? All right. As I go ahead and wait on your questions, I'll start talking about, okay, here we go. So the way to know which is adding and which is subtracting, if initially I have my reactant and initially I have zero product, I can't have negative product. So my change for the product, if it's zero, can't be negative. I can't lose any more than nothing. So that's how I know that I'm going to gain product. I'm going to make it because I have none of it to start. And I'm going to lose reactant because reactant's going to be used up to make that product. So I'm always looking at if I'm starting with reactant and I have no product, then I must lose reactant as I make product, or negative a loss of reactant and a gain of product positive. That answer your question, Alicia? Perfect. All right, so equilibrium constant of bases, just like for acids, but instead of hydrogen, hydroxide is going to be in the numerator. We can make this same assumption as we did last time. Very few hydroxide ions are formed. Therefore, if we have a concentration of our base, subtracting the concentration of the hydroxide is negligible in the overall concentration of the base. What does it mean? A large value for Kb means a stronger base because it means more hydroxide is produced at equilibrium. Everything that we just did before is going to be the same. The only difference is that we're going to deal with hydroxide instead of hydrogen. So let me run through another sample problem for you. So we want to find the pH, not the pOH, that's going to require another step, of a 5 molar copper hydroxide solution, and we're given the equilibrium constant of the base. So if this is my base, copper hydroxide, acids and bases are aqueous, it is at equilibrium with the cation, copper. Copper can have a couple different charges. In this case, I know it's 1 because it's 1 Cu and 1 hydroxide. And hydroxide, we know, is our polyatomic that has a charge of -1. So for our rice table, here's our reaction. Then we need our initial, our change, and our equilibrium. Set up my chart. What do we have initially? We have 5 molar of the copper hydroxide. No copper ions yet, no hydroxide ions yet. What's the change going to be? We're going to lose reactant as we go to make product. That means our equilibrium concentrations are going to be 5 molar minus X, X, X. Again, we're going to make an assumption here. We're going to declare that we're assuming that X is very small, or in other words, X, which is our hydroxide ion concentration. So when I plug into my equilibrium constant of the base, reactants, products over reactants, copper ion over hydroxide ion over the reactant, copper hydroxide. That's going to be X times X, or we can just write X squared over 5. I'm going to drop that minus X because, again, we're making the assumption that our hydroxide concentration is very small and therefore will not affect this. And then we're told that is equal to 4 times 10 to the -5th. We're going to go ahead and solve for x to find out what that is. I'm going to multiply both sides by 5. So I get x squared is equal to 4 times 10 to the negative 5th times 5, which is, I need my calculator real quick. Let's get that out. 4 times 10 to the negative 5th times 5. We get 20 times 10 to the negative 5th. And then we're going to square root that, and we get x is equal to 0.0141. What does this x represent? This is our concentration of the cation and the anion, which we're interested in, which is hydroxide. So if I know the concentration of hydroxide is 0.0141, well, I can find the POH, which is negative log of the hydroxide concentration. So that's negative log of 0.0141, which is 1.85. Now, 1.85 is the POH. What do I do to get from POH to pH? Does anyone remember from our acid-base unit earlier in the notes? How do I get from POH to pH? What do I subtract? Oh, good. Some of you are quick with your memory. So we're going to do 14 minus the POH, which is 1.85. And we get that the pH is equal to 12.1. pH of 12.1, acid, base, or neutral? Excellent. All right, what questions can I answer for you on Kb, or the equilibrium constant of bases? All right, while you're thinking of your questions, I just want to do a quick refresher on buffered solutions. We talked about these in our acid-base unit, and we're going to talk about them again this unit. So a buffered solution is a solution that resists a change in pH when you add an acid or a base. An important example is your blood. Your blood is buffered. Why? Because it is vital to your survival. If your blood pH is less than 7.3, you're having a bad time. If your blood pH is greater than 7.5, you're having a bad time. You want your pH to be right around 7.4. So what is a buffer? It's a weak acid, and it's salt, which is your non-acidic anion. And then, or it can be a weak base, and it's salt. So what is an example of this? We have acetic acid, which is your acid, plus its salt, sodium acetate. All right, and that is it for our notes. I'm going to pause here.